they brought me to Eckhard Hitzer.
Yes.
But the first one. So the title is there. Hitzer from Fukui University in Japan.
Oh no, maybe some light. Okay, good morning. Today I talk about the interactive 3D space group visualizer based on Clifford geometric algebra description of space groups. And for more information, I just recommend you this homepage, spacegroup.info. I do this in close cooperation from the beginning with Christian Perwass, who finished his habilitation at the University of Kiel and now is working for the biggest car part supplier Bosch in the world in Stuttgart in Germany. So as you know, I'm working in Fukui, and the basic idea which leads to this product is using vectors, submit them to the geometric product which generates point groups, which crystallographers call crystal classes. Adding translations gives you space groups. Putting these data via XML files into ClueCalc, the software which Christian pioneered and developed, you get what we call now short SGV, Space Group Visualizer. Now, I want to acknowledge Christian's great engagement because he's doing his programming in his well-deserved vacations and on the weekends and in the evenings. I thank David Hessenes and Jeremy Holt because when there was the last Agaxe conference in Cambridge, David lectured on this idea of expressing crystallographic symmetry with geometric algebra, and I thought this is very nice because as an undergraduate student I never understood what the solid state physicists wanted to explain to me with matrices, and then I knew Christian is making ClueCalc, and I knew just putting these vectors and versors of David into the program should somehow show everything, show all the symmetry. Now we are doing this for 4 years, and you see a kind of nearly finished product perhaps. So some of my students helped with the input of the symmetry data, and in 2006 in New York I met Moe Adoyo, who is now the editor of the International Tables of Crystallography Volume A, and he said, this is quite interesting, please go on. And he put me into contact with Nicola Ashcroft, staff at the IUCI editorial office in Chester, who has also been very helpful. And at this occasion I want to express my great thanks to the organizers of this conference to invite me and give me this opportunity to make this presentation. In all of my talks I acknowledge God, and here I have chosen quotation from Francis Collins, which appeared in 2006 in the Time magazine when he had a big discussion about God with Richard Dawkins, and he said in this dialogue, I do believe in God's creative power in having brought it all into being in the first place. I find that studying the natural world is an opportunity to observe the majesty, the elegance, the intricacy of God's creation. So who is Francis Collins? He's the director of the US National Human Genome Research Institute, so he knows the genes better than anyone else. So I do thank my family because my wife and my children, they enthusiastically support me. Okay, this is what I talk about. Introduction, the geometric algebra approach, point groups, 3D space groups, the geometry and examples, the implementation, then conclusions, and where you get more information. So now, first, the crystal classes, which are the same like the point groups. Here you see the various lattice types from triclinic to cubic, and they have numbers from 1 to 32, all these point groups, so the maximal groups and all their subgroups. And here's the geometric notation, and if you compare it with the standard international Hermann-Morgan abbreviated notation, you see it's much more compact, and as you will see, I hope it's much easier to use as well. Now the geometric algebra approach, we just need to know how to express a reflection at a plane, and then we are done. Then we just multiply. So we have a plane, we have a vector A normal to the plane which characterizes the plane, and then we have a point x which we want to reflect at the plane. It has two components. One is perpendicular to A. I want to use a pointer. One is perpendicular to A, and the other is parallel to A, perpendicular to the plane. If I reverse this component and add it to the perpendicular component, then I arrive at the reflected x prime. And I can express this in geometric algebra using the geometric product with minus A inverse, which is simply A over A squared, so rescaled A times X times A. Now, doing two reflections, I can do rotation. So I have X, I have one plane, this gives me X prime with this first reflection. Then I have another plane, I reflect again, I get X double prime, and this is a double reflection, and here I have what then I call a rotor, here a general rotor. And the angular relationship is that the angle between A and B is just half the angle of the total angle of rotation. Now, I can continue to combine reflections, and I get what is called rotary reflection, or crystallographers also like to emphasize inversion, so they say roto-inversion. That's equivalent. The inversion itself here, if you have three vectors which are perpendicular, or if not, I can just take the wedge product of the three vectors, and I get the inversion. Rotary inversion. So all transformations of two-dimensional and three-dimensional crystal cell point groups, and certainly it can be generalized to higher dimensions. Now, this idea to use this kind of notation, which we will use later on, goes back to work of Cartan and Coxeter. But independently, David Hessnes, found a very nice operative geometric algebra representation, and that's when I think it really has become very useful, not only in this context. So, giving an example of 2D point groups, I have basic geometric figures, and I connect 2 points in the figure and connect to the neighboring vertex neighboring to this one, and then the angles are always right for the symmetry of this figure. And so I shift them to the center because that's the invariant point of the point groups, and then I can use these vectors as I have described it before to generate the point groups, which describes the symmetry of these figures. Now an example, snowflake, n equals 6, here's the number of vertices, and I get the reflections by using these vectors. So R means A times B. I get the 60-degree rotations, and the last one here becomes identity. Now let's go on to the 32 3D point groups, which are also called crystal classes by the crystallographers. So I have these 7 types of crystal lattices, which are well known here. And from these crystal lattices, I always take the elementary cell, and from the cell select 3 vectors. And these 3 vectors completely characterize the cell and its symmetry and generate, as I have described it before, all 32 point groups. So the here you see the cells, the 7 cells, and how to select the 3 vectors. And now this is a notation which was introduced by David in the Agaxe conference, and comparing it to a book of Coxeter and Moser. In the appendix in table 2 they have an isomorphic notation. So he's also arguing with the angles. And so what does it mean? If I just have one index number, it means I have just one vector. If I have an index which is not equal to 1, so not 1 but 2, 3, 4 or 6, then I have two vectors which are at an angle pi over this index. If I have an overbar, the two are together to form a rotor. If I have two numbers, I have three vectors separated by the angle pi over p and pi over q, and I can always choose it so that the third angle is pi half. So the angle between A and C is then pi half. And then overbar over one number means to have one rotor here and the other is still a free reflection, or vice versa, or two rotors. And if it's a closed overbar, it's a rotary reflection or rotary inversion. Okay. And then to get the full notation, you use a brevet prefix to tell if it's a primitive cell or face-centered cell, etc. So that means to have possibly extra translations, fractional translations, and then you add some notation to indicate if there is a glide reflection or a screw, and then you get the full geometric algebra symbol. So the holohedric point groups, these are the maximum point groups, and here I choose the one for the hexagonal lattice. To give you an illustration, beryl is an example, and here is a cell. So I have 6 reflections as I had for the plane two-dimensional space group, point group, and I have the 6 rotations as I had them before, but then I have rotary reflections using this vector c in addition, so just the rotors times c. And I have 6 180-degree rotations also involving A and B and C. That makes altogether 24 symmetry transformations, which can now easily be understood, I think. Then let's go to the space groups, which express crystallographic symmetry. So I have basically, again, these vectors generating reflections and all other point symmetry transformations. And then I add translations in the directions of A, B, and C, and they may possibly be fractions. If I have a face centering or something, then such a number is 1/2. Now, in the so-called conformal model, which also Eduardo introduced for his robotics application of Euclidean space, it's also called double projective or double homogeneous. So that's in the geometric algebra of pseudo-Euclidean space with signature 4(1), so adding 2 dimensions. It goes back to this horosphere concept of Wachter, the assistant of Gauss. Then there are preliminary works, and I finally learned it, and I always refer to this paper in 2001 by Hastings, Lee, and Rockwood. And so this is, we use it for, especially for including translations. So lifting the origin, that's like in projective geometry, so we can represent, for example, arbitrary planes not always passing through the origin. And then we add an extra part. This is E0, and this is called E infinity, and this assures that the square of this vector is 0. And the 2 new vectors are perpendicular to the Euclidean vectors, one for infinity, one for the origin. And as you know, if you have such a mixed signature in general relativity, always you have a null cone. And so we are here on the null cone with all these vectors in a 3-dimensional null cone. And so these are the null vectors like in special relativity we have as well. So benefit already is if we then in this space and this 5-dimensional space calculate the inner product, we get the Euclidean distance squared here. Now we can easily express a plane with this condition here that the inner product